All right, let's do an example with the reference circle. Hopefully you've done the video where we looked at getting the components and you've got the equations. You'll have seen them already a few times, I think, where d equals a sine omega t, v equals omega a cos omega t, a equals minus omega squared a sine omega t, which is often, because that a sine omega t is d, we often can just go minus omega squared d for a. So that's quite a simple one. Now, in my example here, I've got the period's equal to 1.2 seconds. We've got a mass on a spring bouncing up and down. Its oscillations are 0.12 meters in amplitude. And I want us to work out something. A common question would be, so if it's 12 centimeters, I could ask, okay, at the 4 centimeter mark, so at 0.04 meters, calculate the velocity. Okay, so I know I'm going to be using that formula there. Now, that's a good time to use our reference circle. We don't really want to find out the time at which it's at 0.04. Remember, the clock starts at equilibrium point. So, although we've got this equation, omega t, it's easier to do it as omega a cos theta. Remember, omega t equals that. So if we can figure out the angle at that point on the reference circle, this becomes a real easy problem to do. So if we've got a reference circle and we've said the amplitude is 12 centimeters and we want to know the angle when the mass gets to be 4 centimeters vertically displaced, that means that at the 4 centimeter mark, that's 4 centimeters, that's still 12, and we're just asking, what is this angle? And so we just do a very quick calculation with our calculator, which is 4 over 12, right? And we just want the inverse tan on that. So if I do the inverse tan, let me just find my inverse tan on this calculator. Inverse tan of 4, no, inverse tan. I'm so used to doing inverse tans. Of course it's not inverse tan, you should have said so. It's an inverse sine. So inverse sine of 4 divided by 12. And let's see what we've got. And I've got 19.47 degrees. So theta equals 19.5 degrees. Great, we've got the angle. We didn't even have to work out the t. If you want to work out the t though, we'll do that afterwards. But for now we've got the angle and we can easily do now the velocity because it's just omega a cos of that angle, right? Now we've got cos 19.5 degrees, a we know was 0.12. What's omega? Okay, omega. Omega, we can easily work out. This is a formula you need to remember. Omega is equal to 2 pi over t. Okay? Omega is radians per second. 2 pi's are radians, and this is the period. So the period is how long it takes to do 2 pi radians, right? So if we go 2 pi divided by how long it takes to 2 pi radians, we'll get how many radians this little baby is doing per second. So we do our little calculation of 2 pi. Okay, let me just do that. 3.14, 6.28 divided by t, which was 1.2. I've got an omega of about 5.2. So now I can just do my equation for v. 5.2 times 1.2 times the cos of 19.5. So let's do that. 5.2 times 0.12 times the cos of 19.5. And I've got 0.588, about 0.6. and that's a velocity. That was pretty easy. So if that's our velocity, always make sure though that your calculator's in whatever units you're using. So I just did cos of 19.5, right? Now, cos of 19.5 radians is totally different, and a way to find out what your calculator's in is just to do the sine of 30, because the sine of 30 is 1. So if I do the sine of 30 right now, sine 30, it comes up at 0.5. So I know my calculator's in the right units. Don't make those fundamental mistakes. Now, if we actually want to find, so that's finding the velocity. If I wanted to find the time at which it got to that 4 centimeter mark, then I could just go omega t equals theta. Now my theta was 19.5 degrees, but this is radians per second times seconds. It's going to give you an answer in radians, so don't put the angle in degrees. 19.5 degrees is 19.5 divided by 57.3 radians equals omega t. So omega t is equal to that. So all I need to do is do that, divide it by omega, and I've got my t. So 19.5 divided by 57.3, I get 0.34 or something. All I need to do is divide it by my omega, which was 5.2, and I've got my t at 0.065 seconds. Does it seem reasonable? Well, it does if this whole thing is going up, all the way down, and back up again in 1.2 seconds. So that's our first example using a bouncing mass. I'll do another example using a pendulum, but I'll put that in another video.